So now we'll finish up the review chapter and the review material from Appendix A and go through section A-10, nth roots and rational exponents. So what we'll do here is consider square roots, cube roots, primarily. That's the topic, combined with raising to powers, which we've encountered earlier. We have rules of exponents. Those rules of exponents will largely apply as well in this setting of rational exponents. If you dissect very carefully what we've done in the past, we've only considered integer exponents. Well, now we're going to look at fractional exponents, if you like, ratios of integers. So we'll work with nth roots. We will simplify radicals, rationalize denominators, solve radical equations, and simplify expressions with rational exponents. This is quite similar to what we had in the past when we dealt with rules of exponents. The big difference here is we got concerns over square roots and negatives. We can't take square roots and negatives. That has some implications for the rules for roots that we'll encounter here. And that wasn't an issue when we had integer exponents. We could take negative numbers and raise them to any integer power we liked, if they're non-zero. There's a definition, the principal nth root of real number A, where n is greater than or equal to 2, is defined as the nth root of A equals B, means A equals B to the n power, where A and B are both positive when n is even, and A and B are any real numbers if n is odd. So n being an integer, so we're talking about nth roots at this stage. We can only take even roots of non-negative numbers. Whose fault is that? It's the fact you can't take square roots and negatives. Well, we can't take square roots and negatives because we're restricting ourselves to real numbers. Notice also, when you take square roots or even roots in general, you get a non-negative number out. So if A is positive and you take an nth root of A, then B is positive, operating under the principal nth root. It's the meaning of these symbols here. And we've seen this in the past when we've addressed ideas that, remember, square roots are never negative. It's just the meaning of the symbols. Of course, if n equals 2, it's common to drop the 2 and just use the radical symbol to indicate square roots. But square roots are never negative. You may be looking for a negative square root. If so, you'll have to ask for it, like in the quadratic equation. Negative b plus or minus the square root of blah, blah, blah. If you want plus or minus the square root or the fourth root or the sixth root or whatever, where n is even, you got to ask for it. Because the nth root of a when n is even will not be negative. Yet that negative number that also when raised to the nth power produces a, where n is even, might be of interest for physical reasons. Be careful with that, because the meaning of the root symbol in the event that n is even is to give out a non-negative root. The square root of 9 is 3. It's not negative 3. Though you square negative 3 and you also get 9 back out. But that wasn't the issue. The issue was the square root of 9. The square root of 9 is positive. It's positive 3. It's not negative 3. Negative square root of 9 is negative 3. You got to put the negative sign in to get the negative value out if that's what you desire. In the event that n is odd, then we got no restrictions on a and b. They can be any real numbers. In those events, we can take cube roots of negatives, for example, and we will here shortly. Some properties of roots are the following. The nth root of the square root of a to the n equals a, provided n greater than or equal to 3 is odd. The nth root of a to the n is the absolute value of a if n greater than or equal to 2 is even. This we've encountered in the case that n equals 2 before. So when you do raising to an even power, I take some number, raise it to an even power, that'll produce under the radical that'll produce an even a positive number. If n is even, then a to the n is positive. That even exponent absorbs any negative signs that might have been there. And then when you take the nth root, you get something positive out. Well, I can't just ignore those absolute values. I can if a is positive, but if a is negative, I can't. And that's the constraint, and that's the reason the absolute values are required. We saw this several times when dealing with square roots. Holds for general even roots. The nth root of a times b is the nth root of a times the nth root of b. But beware a little bit, this is only going to work when a and b are both positive. If they were both negative, the left-hand side of the equation might make sense. If a and b are both negative, we'd be taking the nth root of, well, if a and b are both negative, their product would be positive. We'd be taking the nth root of a positive number, not a problem. But if a and b individually are negative, we could have some difficulties on the right-hand side of the equation. If n is even, you can't take even roots of negative numbers. So that's the property. We can't take square roots of negatives writ large. We can't even take even roots of negative numbers. If we could use complex numbers, we could. The nth root of the quotient is the quotient of the nth roots under the same condition. All this constraints they put on a and b is to avoid taking square roots of negatives. When you take a fourth root, you're taking a square root of a square root. So it really boils down to the behavior of square roots. And the nth root of a to the m is the nth root of a to the m. Notice the grouping. Here we raise to the mth power first and then take the root. Here we're taking the root and then raising to the mth power. It gives you interchanging of order on whether you extract the root and then use the exponent, or use the exponent and then extract the root. To simplify an expression involving radicals means to remove the radicals for any perfect roots that occur as factors, perfect roots, or things of this sort here. If we had the cube root of 1/8, that simplifies to 1/2, we got rid of the radical. 1/2 cubed is 1/8, so the cube root of 1/8 is 1/2. So simplification involves things like that. We can deal with properties of exponents, which still largely hold, and subtract exponents when we have a quotient, add exponents with a common base when we have a product. So let's look at some examples related to that. Okay, simplify the following. So we'll restate these as we go through and work the problems. All right, you want the fourth root of 16. So we seek a. It's an even root, so it'd be a non-negative real number. Actually, it'd be a positive number because it ain't 0. So we're looking for positive real number a. That, when raised to the fourth power, gives 16. That is, a to the fourth equals 16. A equals 2 works. 2 to the fourth, 2 times 2 times 2 times 2, 4 times is 16. So the fourth root of 16 is 2. It's also true that -2 times -2 times -2 times -2 equals 16, but the fourth root of 16 is not -2. What role does the -2 play in this? Well, they didn't ask us, but the negative fourth root of 16 equals -2. Put a negative on both sides, and there's your -2. It is true that -2 satisfies this little equation right here. A to the fourth equals 16. That's satisfied by both 2 and -2. That wasn't the question. That was something useful in working the question. Remember, fourth roots will be non-negative, so we can't use the -2 for this. It's a little subtle. That's the reason I go on about it over and over and over. The next one asks for a cube root of -1. Well, less will go wrong with the cube roots. Can you take a cube root of a negative? Yeah, it'll be negative, in fact. So this time we're looking for a real number, not a non-negative real number, because we're taking an odd root instead of an even root. We're looking for a real number a that, when raised to the third power, gives -1. That is, we're looking for a cubed equals -1. And no other constraints. There's only one real number that satisfies that. A equals -1, because -1 times -1 times -1 equals -1. So the cube root of -1 equals -1. So it seems that cube roots are easier to deal with. Just a passing comment here. Just as we had a couple of different choices up here of numbers that when raised to the 4th power equals 16, down here, if you'd let me use complex numbers, I'd actually find 3 numbers. 2 of them would be complex numbers though. 3 numbers which when cubed equals -1. Up here, we thought we had 2 choices. You got 2 choices for real numbers that will satisfy this equation. I'm not talking about the original question. I'm talking about this little part of it here. Both 2 and -2 satisfy this. You know, both 2i and -2i also satisfy that, where I is the complex unit, the square root of -1. If you let me use complex numbers, not our problem. But you got 4th power here, you'd end up with 4 potential roots of 16. 4 potential 4th roots of 16. The principal root, the one that the symbols represent, and 3 others, 2 of which are complex. Down here, you want cube roots. Why, there's 3 choices. The principal choice, that's what the symbols represent, and 2 others. And the others are, in this case, fairly complicated, complex numbers. But by restricting ourselves to real numbers, we don't have to deal with that. Just be careful when you take even roots, they're always non-negative. When you take odd roots, they could be positive or negative. You take the odd root of something negative, you'll get something negative. You take the odd root of something positive, you'll get something positive. So the oddness preserves signs, and you can't even take even roots of negative things. You could if you'd use complex numbers, but we ain't doing that. Some more. Next, we'll look at simplifying this expression. So here's the expression. Simplify using the properties we have. All right, let's get the numbers and the x's and the y's all kind of separated from one another. So 3/81, there's an x and an x to the 4th. There's a y squared and a y squared. Let's separate those out and be very careful when canceling things. First, 3 divides 81, what? 27 times? That's right. So 3/81 reduces to 1/27. X over x to the 4th. We could cancel this x with one of those, leaving us with 1/x cubed. Okay, we canceled an x. Do I need to write x doesn't equal 0? Yeah. Well, I did. There's an x in the denominator. So this term here contains the information that x can't be 0. I don't have to write if x doesn't equal 0. Of course x can't be 0. It's right there in the denominator. So it can't be 0. You can't divide by 0. Let's cancel the y squares. This is a little different. Y squared divided by y squared, that equals 1 if y is not 0. Do you see, in this previous expression, do you see that y can't be 0? Yeah, because it's there in the denominator. X can't be 0 either because there's an x in the denominator. How much of that information is present in this expression? Ignore the if part for a second. Well, x can't be 0 because there's an x in the denominator. But if I just look at this, no reason y can't be 0. There's not even any y's in this. But there is in the original expression. The original expression does not equal simply this. It equals this, provided y is not 0. Did you say y is not 0 in the beginning? Effectively, by having a y in the denominator. Then you better say it at the end. You're not saying it by having a y in the denominator, so you got to pencil it in by hand. The x behaves differently. X can't be 0 because there's an x in the denominator. Yeah, even after cancellation, there's still an x in the 0. So I don't have to write if x doesn't equal 0. Doesn't hurt anything, I guess, but I don't have to explicitly write that. I do, the important thing is I do have to explicitly write y does not equal 0. That's not implied by this expression. All right, so that's just the cancellation. We haven't even dealt with the roots part yet, and that's the new stuff. By the properties of roots that we just stated, then we're left with the cube root of 1/27. We'll separate that from the cube root of 1/x cubed. Hey, 1 over 27. 27 is 3 cubed. So 1 over 27 equals 1/3 cubed. And of course, 1 over x cubed equals 1 over x cubed. Right? 1 over x cubed equals 1 over x cubed. Awkward to verbally state. Easy to state in terms of math symbols. That's part of the beauty of math symbols. So what we're dealing with here is the cube root of 1/3 cubed. Well, that's just 1/3. Here we're dealing with the cube root of 1 over x cubed. 1 over x cubed. Well, you take the cube root of something cubed, you get the something. The something in the first case is 1/3. In the second case, it's 1 over x. So we get 1 over 3x. So the original expression is the same as 1 over 3x. Don't forget the y doesn't equal 0 part. Right? I started a new sentence here. We were looking at this last expression and not dealing with this part of the information. So I haven't written anything wrong here, though I could slap if y doesn't equal 0 throughout all of these. I don't need to. I do at the end, though, because I'm tying it back to the original expression. Original expression, y can't be 0. Y can't be 0 here as well, because they're equal expressions. So subtle stuff. This subtle stuff will play a huge role in Calculus 1. Next, we were asked to deal with the cube root of 3 times the square root of 10 to the 4th power. We want to reduce the exponents as much as possible. So that gives us cube root of 3 to the 4th power times the square root of 10 to the 4th power. When I have cube roots cubed or square roots squared, I can simplify things. One of the properties of note A.10.A. Well, we've got cube root of 3 to the 4th power. So let's pick 3 of them off and have the cube root of 3 cubed, and there's a 4th one left. Right? Notice the different roles that the 3's play. The 2 big 3's are inside the square root function. Inside the cube root function. The middle size 3 is an exponent that says cube this stuff inside. And the smallest 3's on the radical, those say take a cube root. So we had some stuff to the 4th power. Here we've got that same stuff to the 3rd power and the 1st power. Add those exponents on that stuff, and that'll take you back to a 4th power on the stuff. Stuff being the cube root of 3. Why would you do that? Oh, I know what the cube root of 3 cubed is. It's 3. That's what cube roots mean. About the square root of 10, let's write that as a square root of 10 squared times a square root of 10 squared. Now, when you multiply these together, you'd add exponents and get the square root of 10 to the 2 plus 2 power equals 4. So they're certainly equal. Why would you do this? So we can simplify this to 3. We can simplify this to 10. And this one's also 10. The cube root of 3 cubed is 3. That's what cube roots mean. The square root of 10 squared is 10. So we'll substitute those in. The original expression we had written like this. What equals this? We substitute in for this first thing 3, substitute in for this thing 10, and this thing 10. So we get a 3, a 10, and a 10. The cube root of 3 from right there, we're still stuck with it. And so we get 3 times 10 times 10, that's 100, 300 times the cube root of 3. And there's what that one, what number 30 simplifies to. So the goal is reduce things as much as you can. Make the exponents integers if you can. Next was to deal with this expression. Simplify 2 on the square root of 12 minus 3 on the square root of 27. Okay, square root. So I'm looking for perfect squares. So we can combine the square root stuff with the squaring stuff to get the stuff out. What's up with 12? 12 is 3 times 4. No, 12 is 3 times 2 squared. I'm looking for square stuff, so I can take square root of square stuff. 27, well, we saw that was 3 cubed before. Well, 3 cubed, that's 3 squared times 3. So I can get a square root of something squared. There'll be some stuff left over. Some stuff left over in this one too. So we can take 2 square root of 12 minus 3 square root of 27. Rewrite it as given, as we did. let's take the square root of 2 squared and the square root of 3 using the property of roots. Here, let's take the square root of 3 cubed and write it as a square root of 3 squared times another square root of 3, property of roots again. The square root of 2 squared, strictly speaking, it's the absolute value of 2, or 2 itself. The square root of 3 squared, strictly speaking, is the absolute value of 3, equals 3 itself. So this becomes a 2, this becomes a 3, and then we can simplify down upon substituting for this a 2. So here's the 2 out front. You're left with a 2 on the square root of 3 inside. This became a 3. There's the 3 out front, and we had a 3 and a square root of 3 left. There's the 3 and the square root of 3. All right. Gee, we could factor a square root of 3 out of both of these and further simplify. We'd have 2 times 2 times the square root of 3. That'd be 4 times the square root of 3. Here we've got negative 3 times 3. That would be minus 9 times the square root of 3. So factored the square root of 3 out and did the multiplication of both of these in a single step. 4 minus 9 is negative 5, and we're still stuck with the square root of 3. So we didn't get rid of all the square root stuff, just like in the previous one, but we got rid of one of them. We've simplified it as much as we can. Next question was simplify this product. Okay, we got a square root of 5 and a square root of 5. We'll multiply. These are product of 2 binomials, so we'll have to FOIL it. Those 2 square root of 5s will get together, ultimately to produce a 5. And some other stuff will happen. So we got to FOIL it because it's a product of 2 binomials. First, outer, inner, last produces these 4 terms. Trust me, pause the video and convince yourself that the arithmetic is correct. Here we've got the square root of 5 times the square root of 5. That's the square root of 5 squared. Of course, that's going to simplify to 5 in the next equation. Here we've got a square root of 5 times 3. Here we've got a negative 2 times the square root of 5. We can combine those as a single square root of 5 term. We'll have 3 minus 2. 3 minus 2 square root of 5s. Factoring a square root of 5 out of these 2 terms. We're still stuck with a square root of 5, it looks like. And last produces negative 2 times 3. So there that is, that's negative 6. So we get this at the next stage. Square root of 5 squared is 5 itself. 3 minus 2 is 1. So we get 1 square root of 5 minus 6. Do the subtraction. 5 minus 6 is negative 1, and you're still stuck with a square root of 5. So there's how to simplify that one. It's a single expression in a sense versus being a product of 2. So FOIL it, multiply out, and then deal with the arithmetic that arises. Back to the notes. When radicals occur in quotients, it's customary to rewrite the quotient so that the denominator contains no radicals. This process is called rationalizing the denominator. The identity a plus b times a minus b equals a squared minus b squared, that's useful in getting rid of square roots. Right? The right-hand side contains stuff that's squared. So if a and b were the square roots of something, we could get rid of those square roots if we could manipulate a and b to produce this kind of thing. I'm motivating what we're going to do in the following 2 examples. Back to the examples. Okay, they want us to rationalize the denominators in these 2. The first one is much easier than the second one. What makes this one complicated is there's addition in the denominator, and there's not in this one. All right, you want a rational denominator? To get a rational denominator, we multiply by a version of 1 that eliminates the radical term in the denominator. We'll do that in both of them. It's easier in the first one than the second one because of the addition. So we've got negative square root of 3 over square root of a. Let's multiply that by 1. That doesn't change anything. And my favorite version of 1 at this stage of my life is square root of 8 over square root of a. Why would you do that? You can't argue with it. It's true. It's multiplied by 1. Well, then in the denominator, we'll have the square root of 8 times the square root of 8. We'll have the square root of 8 squared. And that'll get rid of that square root in the denominator. As you do that, some other stuff happens in the numerator, so we'll keep track of that. But we were trying to rationalize the denominator. Mission accomplished. Square root of 8 squared is 8. So it worked. But some other stuff is happening in the numerator. Square root of 8, let's see, that's 2 times x squared. 8 equals 2 times 2 squared. It's 2 cubed. I'm looking for squares under square roots to further simplify things. So let's write 8 is 2 times 4, 2 times 2 squared. Now we've got the square root of this times the square root of that. That's the product of the square roots. Okay, we've accomplished something here. The square root of 2 squared is 2. So we'll replace this with a 2. There it is. The square root of 2 is still there. The square root of 3 is still there. And a negative sign is still there. Right, this negative sign is left over from the beginning. We can simplify here. 2 divided by 8 is the same as 1 divided by 4. So we did some cancellation there. There's a negative sign. There's a square root of 2. There's a square root of 3. The 2 went into the 8 to produce a 4. There's an answer. If you like, I can combine these two and write this as the square root of 2 times 3. It's the square root of 6. So negative square root of 6 over 4, it's equivalent to that. And the denominator is rational. That was the question. Let's do another one. But this next one's trickier because of the addition. So deal with this. Rationalize the denominator. To get a rational denominator, we multiply by a version of 1. But that's all we can do. You change the problem. If you just square the denominator or something like that, can't do that. That changes the whole number, the whole expression. But we multiply by 1 in a way that eliminates the radical term in the denominator. We're trying to get rid of that square root of 5 in the denominator. I really want to square some stuff. I really want to square that. If I could just square this all by itself, we'd be good to go. But you can't do that, or you change the expression. Again, we'll take inspiration from this little formula here. So I want to view this square root of 5 plus 4. I want to think of it as like this. So A is the square root of 5 and B is 4. A is the square root of 5. That's the one that's angering me because it's got a square root in it. We got to get rid of it. Well, if we multiplied by this, we wouldn't be dealing with A and B. We'd be dealing with A squared and B squared. And if A is the square root of 5 and we get the square root of 5 squared, well, that's just 5. And that'll get rid of the square root. So here's the procedure. Take what was given, multiply it by 1. What version of 1 do you like? Well, something that looks like this. So we're going to take the square root of 5 minus 4 divided by itself, and that's 1. So we're not changing anything. The equality still holds. And when we multiply this out, because this is of the form A plus B times A minus B, it's of this form here, we'll get the first one squared plus the second one squared. And when you do that, the square root on the 5 will disappear. And some stuff happens in the numerator. The question was rationalize the denominator. So I guess I'm fairly uncaring about what happens to the numerator. Fix the denominator so there's no square roots in it. Okay, this will do it. You can't argue with the validity of this. You could argue with the motivation of it a little bit. Here's the motivation, as explained. I'm taking my lead from this little formula here. Multiplying the denominator by just the right thing will produce some perfect squares. And that's how we'll get rid of the square roots. But of course, I can't just multiply the denominator by something. I need to multiply by 1, and that'll affect the numerator as well. So when we FOIL this, maybe rewrite it as given here. So if we'll FOIL this, the center terms cancel. It's of this form here. You'll get the first one squared minus the second one squared. First term is square root of 5. Second term is 4. The negative here manifests itself as a negative between those two. And in the numerator, well, we'll talk about it later, I guess. We get -3 times that square root of 5 minus 4 thing. Just rewriting again, taking care of the denominator. And this is the big step because this is where the square root symbol disappears. Square root of 5 squared, that's just 5. 4 squared, well, that's 16. And smiley emoji, the denominator is rational. So we've accomplished what they ask us to do in terms of rationalizing the denominator. Let's simplify it a little bit. We also distributed the -3 in that step. So we get -3 square root of 5 plus 12, 3 times 4. 5 minus 16, that's -11. Can't really do anything with the numerator. Here's a fine answer. I mean, it's got a rational denominator. I went one step further and got the negative out of the denominator to make the denominator, I don't know, even simpler, arguably. But we'll factor a negative out of the numerator. So this would be -3 on the square root of 5 plus 12. That's the same as negative quantity 3 on the square root of 5 minus 12. Distribute the -1. This term will become negative times negative. Then we'll have a plus 12 on the right upon distributing. These really are equal. And now we can cancel the negative signs to write it like this. From my perspective, this is a fine answer. You don't need to do this. They ask for a rational denominator, and you've got it here. If you check your answers in the back of the book, this is the kind of thing they tend to do. So you look at these, and they don't look exactly the same, but they are. They're just different versions of the same thing. And both have rational denominators. So both are legitimate questions or legitimate answers to the question, rationalize the denominator. Let's do another one. Solve this equation. Square root of 12 minus x equals x. All right. This is our first equation involving square roots, I think. Square roots of variables, at least. First, x is a square root of something. It's a square root of this, right? X equals a square root of something. Well, square roots are never negative. So from the very fact that x is a square root of something, I know x is greater than or equal to 0. I know x is non-negative. Keep that in mind. We're going to square both sides. If we square both sides, that'll get rid of the square root on the left. But remember, x is greater than 0. Square both sides, we'll get this left side squared and this right side squared. But whether x was positive or negative, or for that matter, whether this square root was positive or negative, that's lost when you square both sides. If there had been a negative sign here, you'd end up with the same thing. The squaring would absorb that negative sign. We're introducing different information. I've warned you about this. We're looking at extraneous roots potentially. But squaring both sides runs the risk of introducing extraneous roots. So we've got a square root squared. Well, that will produce simply the quantity, 12 minus x, in that order. If it's the other way around, a square root of something squared produces an absolute value. That's not what we have here. Right-hand side is x squared. So that's equivalent to 12 minus x equals x squared. Let's rearrange it. Take the x to the other side and take the 12 to the other side. So we'd have x squared plus x minus 12, x squared plus x minus 12 equals 0. Factor that. Find your AB that multiplies to give 12, I'm sorry, negative 12, and adds to give positive 1, the coefficient of x. At this stage, you should be fairly experienced with that. We find it's x minus 3 times x plus 4. Left-hand side factors, it's set equal to 0. So just looking at this equation, we'd have the solutions 3 or negative 4. X equals 3 or x equals negative 4. But remember this, x is greater than or equal to 0 because it's a square root, and square roots are greater than or equal to 0. Negative 4 doesn't work. It can't possibly be negative 4. It must be 3. X is greater than or equal to 0. The only valid solution is X equals 3. Plug that in. 12 minus 3, square root of, that would be the square root of 9, which is 3, which is what X is. If you plug negative 4 in, you get 12 minus negative 4, that'd be 16. Square root of 16 is positive 4, not negative 4. Right, so if I plug the negative 4 in on this side, the left-hand side becomes positive 4, and the right-hand side becomes negative 4. Plugging X equals negative 4 in. Well, they only differ by a negative sign. Yeah, well, they ain't equal, and that's the problem. And the fact that they only differ by a negative sign, that's not a coincidence, because when you squared both sides, you lost the sign information of both sides. So that's kind of the reason that you get negative 4 versus 4 and this X equals negative 4 substitution. And what's happened is by squaring both sides, you've lost negative signs. You've encountered extraneous roots. We talked about that several sections ago. So X equals negative 4 is an extraneous root. What you could do is square both sides, see what that produces, and then check all of these individually. That's an alternate way to find whether they're valid solutions or not. Back to the notes. All right, final thing from chapter A, Appendix A. We now give meaning to rational exponents using radicals. So we're actually finally defining something more than roots themselves. You're no doubt familiar with the fact that a square root is a 1/2 exponent. If A is a real number and n greater than or equal to 2 is an integer, define a to the 1 over n to be the nth root of a. Like I said, square roots are the same as exponents of 1/2, provided that nth root of a exists. What do you think that means? No square roots and negatives is what they're getting at with this. If n was 2 and a was negative, we'd have a problem. We can't take square roots of negatives or fourth roots and so forth. If a is a real number and m and n are integers containing no common factors with n greater than or equal to 2, then define a to the m over n as the nth root of a to the m power, or the nth root of a to the m power, provided this exists. All right, so that's about no square roots of negatives. And this no common factors stuff simply means you've reduced the fraction. M over n, you've reduced that fraction. No common factors between m and n. So by definition, raising a real number to an m over n power is taking an nth root, the number in the denominator, and raising it to an mth power. Order apparently doesn't matter. And it's a definition, you can't argue with it. So this is how rational exponents are defined. Oh yeah, provided there's no square roots and negatives that pop up in this stuff. And we could, instead of writing roots all the time, we could deal with exponents. And that's what the last few examples are about. So let's go through those. Simplify the expression. Express your answer so that only positive exponents occur. Assume that the variables are positive. So that's their blanket statement to say, don't worry about square roots and negatives. So assume all this stuff is defined. You got to worry about division of 0, potentially still. I see some division in this one. Okay, negative 25 to the negative 1/2 power. Okay, a negative exponent indicates a reciprocal. So when we have 25 to the negative 1/2, take that 25 to the denominator. It's 25 to the negative 1/2 first, and then there's a negative sign out front, right? Orders of operations is do the exponentiation first. So the exponentiation happens before the negative sign out front occurs. So we get the -1 in the numerator, 25 to the negative 1/2, negative reciprocals, negative exponents mean take reciprocals. So the 25 to the negative 1/2 can be rewritten as 1 over 25 to the 1/2. There's the -1 out front. Exponent of 1/2 indicates a square root. So 25 to the 1/2 is equivalent to the square root of 25. Square root of 25. 25 is 5 squared. That square root is 5. It's in the denominator. Numerator contains -1. And there's a simplification of negative 25 to the -1/2. Produces -1/5. Let's do one with variables. Okay, we got properties of roots and properties of exponents. They give us the following. So we're dealing with xy to the 1/4 times x squared, y squared, quantity to the 1/2, x squared y quantity to the 3/4. These are multiplied together before the 4th root was taken as well. Let's put those exponents on each of the constituent pieces. So we'll have x to the 1/4 times y to the 1/4, property of roots. 4th roots is what we're dealing with here. Behaves like this. We'll have x squared to the 1/2 times y squared to the 1/2. It's a distribution type property, distribution of the exponents. Same thing down here. We'll have x squared to the 3/4, x squared to the 3/4, y to the 3/4. Okay, so we got rid of the parentheses. Well, not all of them, I guess, but we got rid of the parentheses but between the x's and the y's. We've isolated powers of x and powers of y in this. Let's go one step further. Under these circumstances, properties of exponents, you multiply. So we get x squared to the 1/2 power. That would produce x to the 1 power. Actually, that'd produce the absolute value of x. But they've given us this loophole that all the variables are positive. So no absolute values are necessary in that. Let's see, it was this x to the 1 right here. Same thing with the y squared. Y squared, square root of is y itself, provided the variable is positive. The x squared to the 3/4, multiply, that'd give us x to the 3/2. 2 and the 4, simplify. Y to the 3/4. So multiplying exponents as a property of exponents tells us produces this. All right, now we'll add exponents for x's and y's, won't we? Oh, not yet. Next, let's take these denominators and put them in the numerator. So x to the 3/2 in the denominator is equivalent to x to the -3/2. Y to the 3/4 in the denominator is equivalent to multiplying by y to the -3/4. So let's see, we had an x to the 1/4 and an x to the 1. Right, there's the denominator x term. We had a y to the 1/4, a y to the 1, y to the 1/4, y to the 1, and there's the denominator term. Now it's a matter of adding exponents. So we'll have x to the sum of these three, that is x to the 1/4 plus 1 minus 3/2, y to the sum of these three exponents, 1/4 plus 1 minus 3/4. As stated, do the arithmetic, that'll produce x to the -1/4, y to the 1/2. Well, they say they wanted positive exponents, so we'll have to take that x to the -1/4 and move it back down to the denominator to produce y to the 1/2 divided by x to the 1/4. That's the simplified version of that. So it's just a matter of multiplying exponents when appropriate, given the rules of exponents, and adding exponents or subtracting when we have quotients. We actually took those denominator things and wrote them in the numerator, so it was nothing but addition. Sometimes it was addition of negative numbers, so there's your subtraction. That produces this. Let's do, yeah, this is the last one, I think. Let's consider this expression. X is greater than or equal to 3/4. What's up with that? You see this? 4x minus 3 to the 1/2 power. So it's 4x minus 3 square root of. If x is greater than or equal to 3/4, this is non-negative. Plug in 3/4, you'll have 3 times 3/4. That's 3 minus 3 equals 0. This will be 0 when x equals 3/4. And when x is greater than 3/4, this will be positive. This goes in to avoid taking square roots of negatives. One can check, I leave it to you to explore this. These will also involve positive terms for such x values. though it looks like we're taking cube roots on these. But the reason they've given you this condition is there's a square root of 4x minus 3 right there. You know, there's another one right there, the 1/2, the 2 in the denominator of the exponent, that's got a square root as well. These are cube roots, so not even an issue. Instructions are factor and express your answer so that only positive exponents occur. Okay, well, there's a 6 term in both of these. We'll factor that 6 out. There's a 6x plus 1 term here and here, but this one's to the 1/3 power and that one's to the 4/3 power. And there's a 4x minus 3 term here and here, but this one is to the 3/2 power and this one is to the 1/2 power. So we'll factor out the lowest power of those binomials, 6x plus 1 and 4x minus 3. So we've got 6x plus 1 to the 1/3, 6x plus 1 to the 4/3. So we can factor the 1/3, the smaller exponent. We can factor that out. 4x minus 3 to the 3/2, 4x minus 3 to the 1/2. That's the smaller of those two exponents. We can factor that out. So we'll factor 6x plus 1 to the 1/3, 4x minus 3 to the 1/2, factor those out along with a 6. So out front, we'll have a 6, 6x plus 1 to the 1/3, 4x minus 3 to the, oops, here's the factoring, excuse me, this is a restatement of the original question. Factor these out. Here's the 6, here's the 6x plus 1 to the 1/3, here's the 4x minus 3 to the 1/2, big parentheses. What's left? First term, we took the 6 out, we took the 6x plus 1 to the 1/3 out, we took some of this out and some of it's left. We took 4x minus 3 to the 1/2. You had 4x minus 3 to the 3/2. We took 1/2 away. That'll leave us with 3/2 minus 1/2, which of course is 1, which we'll have down here. Over here, we took the 6 out. We took the 4x minus 3 to 1/2 out. So we took the 6 and all of this and some of that. How much? 6x plus 1 to the 1/3. So we'll have 6x plus 1 to the 4/3 minus 1/3. Subtract those exponents and factoring like that. We get that much left. 4/3 minus 1/3 is also 1. So next step, here's the 6. Rewrite that term. 4x minus 3 to the 3/2 minus 1/2 is 1. We'll write the exponent this time. 6x plus 1 to the 4/3 minus 1/3. It's just to the first power. We'll write that out. We got it factored. We can combine these two terms. Textbook example A. So 4x plus 6x is 10x, minus 3 plus 1 is minus 2. And here's we've reproduced the other terms outside of the parentheses. And that's as simple as we can make that. Notice we've simplified, I guess the instructions were factor, and written it, factored, and then simplified. It's a product now, so it's been factored into these constituent parts. And that is all from Appendix A. That's all for nth roots, rational exponents. The big warnings on some subtle things are you can't take square roots and negatives because I won't let you. We're not doing complex numbers. I'd love to take square roots and negatives. Come back and see me in a few years and we can do that. And we can't divide by 0. Nobody can. There's people living perfectly happy lives taking square roots and negatives. But they ain't doing it in our pre-calculus class. But nobody is out there dividing by 0. That's just not a math thing. You can't divide by 0. It's an undefined, meaningless concept. So there's two things we don't do at this stage, but for really different reasons. On down the road, there'll be some other things we can't do in Precalculus 1. We can't take logarithms of 0 or logarithms of negatives. In some other classes, maybe you can take logarithms of negatives. You can if you use complex numbers. You can't take a log of 0. It's related to division by 0, so it's still forbidden. But that takes care of the review material. So onward to chapter 1, and we'll start the body of the class. I will see you there. Have a nice day.